the next few sections, I'm going to go over some performance analysis. We'll start with doing some performance analysis on NUMA type server architecture, and see how in real life, when you have such architectures being deployed in real life, what kind of latency and bandwidth you actually can achieve from the DRAM. And I'll explain later why that is important. Then I'll dive into some of the theory of operation, how it works, how it's deployed, and how it fits in the overall system architecture. And finally, we'll do some, we'll go high level, I'll touch a little bit about the hardware and software integration, how they both work together to provide this Memory1 solution as a memory expansion, working in conjunction with standard memory to provide a much larger memory footprint for applications. So let me start by listing or discussing or saying, why do people usually say flash is bad as memory expansion? Like when you say using flash as memory, a lot of people like it's frowned upon. Like it's not something positive. There's always negativity about it. And I just listing here 5 of the top reasons why people do not think flash is a good cannot be used as an expansion for memory. First one is it's slow. It's 1,000 times slower than memory. DRAM is nanoseconds. Flash is microseconds. And latency, it's microseconds of latency in flash versus nanoseconds in for DRAM. Bandwidth, gigabytes, tens of gigabytes for DRAMs and few gigabytes for flash. Infinite endurance for DRAM, limited endurance for flash. Applications do not today know how to exactly leverage flash as memory as is, and of course, not being byte accessible is another reason why people do not think flash is a good replacement or is a good cannot be used as a memory expansion. So the plan is to show that through this presentation how that all these negative attributes actually can be addressed using Memory1 as a solution, as a software and hardware solution. And as a matter of fact, as you'll see in the next few slides, it turns out that actually in real life, in a enterprise type multi-socket server architecture, most if not all of these claims actually disappear, as I'll show in the next few slides. So let's first start by just go over a standard multi-socket enterprise server. And let's talk about NUMA. What is NUMA? Most of you probably are aware. It's not non-uniform memory architecture. What does that mean? What it means is with multi-socket systems, data access seen by processes running on any socket may vary depending on where that is being accessed from. Every socket has local memory and has remote memory. If a process is running in the first socket and it's accessing data from its local memory, the latency it observes is substantially lower than that it observes if that data happens to reside on the other socket. Likewise, if a process running on this socket and is running a lot of memory traffic, and that memory traffic happens to be on this local to this socket, the bandwidth that it will observe is going to be substantially higher if that bandwidth is if that data actually is residing on the remote socket. So, and that's of course because these two sockets are linked through what's called a QPI bus, interprocessor bus, that guarantees coherency between the two sockets. Now, this is for a dual socket. The problem even becomes more complicated and more visible if you start looking at a quad socket system where you have 4 NUMA nodes, all connected through yet another QPI bus. And similar to the dual socket system, or unlike the dual socket system, the maximum number of hops you can have in this architecture is 1. So you can either data can either be local or can be remote. In the quad socket system, there's yet another remote location. There's the current, there's the neighbor, and then there's the 2 hops away socket. So you can have up to 2 hops of QPI stations for data to be accessed from one socket to another socket. And now, why is this important? Why we're looking at the dual socket and the quad socket? What we have seen in a lot of the applications that we're addressing, that a lot of people who go to quad socket, they do not go to that architecture because they need the CPUs. All what they need is the memory. They need 1 or 2 terabytes of memory. But there's no way they can actually achieve that on a dual socket. So, however, the capacity is important for them. So what they do, well, they bite the bullet and buy a quad socket system to get the 2 terabytes, and most of the CPUs are idle, but they got the capacity. So that's one situation. The other situation is a lot of the guys who are actually using dual socket system, they wish if they can find an economically viable solution that can allow them to have more capacity within the server, so that they can, for example, cache more memory, cache more data, and as a result, for example, reduce the traffic going to the backing storage. However, and going to quad socket is prohibitive cost-wise. Therefore, if one can provide a solution that can provide the capacity of the quad socket system in the dual socket system, that can achieve a performance that is as good, close enough to the performance you can get in a quad socket system, but in the dual socket system, that's a win-win for in both situations. All right? And that's where Memory1 comes as a solution. Now, I'm going to go through some measurements that we have performed at Diablo that will show what is it that we're targeting, what levels of performance and latency we need to achieve in order to be good enough for applications. And address the fact that people think DRAM is perfect. DRAM has nanoseconds of latency. DRAM has infinite amount of bandwidth. All right? So let's put that into test. What we did is we created 3 test environments. And we used an off-the-shelf standard memory test benchmark called Stream. I'm not sure how many people are familiar with it. It's a very simple test. All what it's doing is reading data from memory, doing very simple operations on it, like add, scale, something like that, and then writing back to memory. So very, very light in CPU, very heavy in memory. And it's designed to test the memory bandwidth and performance. And it's single-threaded, and the way you run it is you run 1, 2, 3, 4, and you just keep scaling up the number of instances, and you just see how the memory bandwidth scales as you add more instances of that benchmark. So we use that test to really find out what's the real performance that DRAM can provide in a quad socket system. We did 3 scenarios: the local scenario with distance 0, adjacent, and the worst scenario. In the local one, what we did is we physically pinned the process, the stream benchmark process. We pinned it into the NUMA node, and there are Linux attributes that will allow you to pin the data associated with the process to a NUMA node. All right? So we pinned the process and its data within the same NUMA node. Okay? And we call it local test or distance 0. The second scenario, what we did is we pinned the process on one NUMA node, and we pinned its data to the neighboring NUMA node, forcing all transactions of memory to have to go through the 1 hop of QPI. The third scenario, which is the worst case, is actually pinning the process on one NUMA node and its data be 2 hops away from where that process is, and of course that means every data transaction has to go through 2 hops of QPI bus. And as expected, and then what we did is actually sweep the number of processes that are running. As expected, with a distance 0 or local mode, the bandwidth of the memory scaled very nicely all the way to just shy of 60 gigabytes. So claim that DRAM bandwidth is infinite, check, it's good. However, if you actually now look at the performance of the second scenario, which is data is being fetched or being accessed through the adjacent NUMA node, bandwidth drops more than 50%. We're talking about just shy of 30 gigabyte now. The bandwidth saturates at that level. Even worse, when you go through 2 hops, you're down 80%. You cannot get more than 10 gigabyte out of pure memory bandwidth text.
Isn't there like an E5 4680 or something like that, or 4650 that has 3 QPIs rather
That's
than 2?
an EX.
So in that case, it'd only be a maximum of 1 hop.
That's 15, that gets 15 gig.
Yeah.
Actually, the way we found this, if you permit, on memory channel storage, we went to market with Lenovo on their 3850, which is a 4-socket EX Haswell platform, which is the state-of-the-art, let's say. And that's an EX processor. An EX processor is designed to scale, and it's a star, right? So basically, they connect to the adjacent and then the other guy.
Yeah.
And we spent about a month trying to understand why the hardware that we had, if we ran our MCS modules, we had 8 on every processor, we could scale up to 32 gigabytes of traffic to the flash, okay? Which is what the theoretical maximum at the time for the UltraDIMM was. But if we tried to rate it, we couldn't get more than 12 or 13 gigabytes. And it turned out the way we stumbled on this kind of limitation, so to speak, at the time it was a limitation, but now we kind of, I'll kind of link it in a minute. On the EX platforms, it's about 50% better, but what happens is if, for example, we were running in a RAID where the page to a certain application, even in storage, could come from anywhere on those processors, which is kind of how it's supposed to be designed. The best we could get was something in the order of, 3 million IOPS or something like that, when the hardware should have been able to do 6, 7. And it turned out that the reason that we were limited was the interprocessor bus. The EX platform this is an EP, right? So this is the same processor that's kind of in the 2-socket, except configured for a 4-way, okay? It is better, but by 50%. Now, what we ended up realizing is that the reason that this is important is because this brings about the notion of a page of data that an application wants that is far away. Okay, and so if you don't mind, I'm going to turn it right back to you, but this is really fundamentally important. The thing that kind of tipped us off to this whole concept was, okay, well, Christ, we thought, okay, it's memory, it's the fastest thing on the planet, but there's like real limitations in the end, right? In terms of how things are interconnected. And let's face it, the new processors that Intel has are actually, amazingly, this exact configuration, but in 2 sockets. So if you analyze a Haswell processor, it turns out there are 4 home agents, 4 nodes. 2 of these are in 1 socket, 2 of those are in another. So they literally, did an SoC integration of this architecture. And that's how we get up to 18 cores on 1 physical socket. Like, in the end, there's the law of physics and interconnect and whatever. So this is a really important concept. Okay. What we learned was, hey, in the world where people are running in the cloud or on the internet, their systems are running hundreds of threads. Applications are time sharing those CPUs like crazy. Of course, right? That's how you use what you buy. Well, it turns out that you have no way of knowing that a page here is going to be needed by a thread there, Okay, there's no way that happens in the cloud. And so we said, okay, well, it turns out that if our page was kind of here, conceptually, it's in the flash. It's kind of far. It's 100 microseconds away. Right? So all we got to do is get that page somewhere where the application is running, can use it, and then it goes. It's not really that different. It's actually probably better in some cases than having to go through the cache coherency problems of the processor and have it work. And so the notion is, this is to show that there's a reality of pages that are close and pages that are far, even today in the processors of today. And so, you know, you can see a pretty dramatic reduction here. And so we use this to guide ourselves on what type of bandwidth do we want to target for the product, what type of latency is really expected by the application, and it turns out that we're now kind of in the zone. Okay, that's why this analysis is important. It's more to illustrate the realities of the server, because the DRAM is not quite as fast as you think, and our flash is actually faster than you think, and then the software has to close the gap the rest of the way.
So I have the question because I don't understand. So you are presenting as a 4-processor architecture, okay, but most of the hyperscale end users are using 2-circuit architectures.
Absolutely.
So, at the end of the day, we are always in the first and in the second case. So the worst scenario is 30 gigabyte per second. If I have an average, it's 40. At least 40 gigabytes per second.
Yep.
So actually, there is a huge difference between RAM and between your memory. And so I don't understand why you are choosing to show us 4.
It's about the amount of memory you can put in your system, right?
Yeah.
In the end, it will go to 2, but they can put much more memory in it.
Yeah. And actually,
No, I understand.
No,
but actually, this is not how modern data centers are organized
no,
today.
yeah, sure.
So,
no, you're raising an excellent point. What we're trying to show here, okay, is somebody who does want to buy a server with lots of memory, they're going to get something closer actually to somewhere between this, okay? And they're very happy, actually.
yeah.
Okay, because really the data is in memory and it runs very fast. And we're going to show you later, for example, we have results on Spark, which is a sort. You can see that because you have a terabyte of data, very little data, only 100 bytes, but billions of them that are actually in memory, that machine can sort that data in tens of minutes. It breaks down. So what do you need to do? You need to actually run 10 machines to sort that data, or 20 machines, and now you have it's worse than this, you have the network between the machines. Okay, so it's about how much data can you fit on the server, and it's about consolidation. So if we're running, for example, I'll show you later, Redis, on a 2-socket 1 terabyte system, we can run a terabyte of Redis data and databases, or you run it on 10 servers, right? So this isn't the DRAM. If you had a terabyte of DRAM in any server, it will blow the doors off a terabyte of Memory1 on a pure benchmark. Nobody's claiming the opposite, right? Go back to the slide. It's faster, big time, right? What we're trying to explain is that, think of it a little bit differently. If you could fit the data near the processors, even if you compromise your bandwidth and your latency by the amount that we're describing, your system will run like stink. Okay, and so we're trying to show that, and by the way, most applications, even though they have 40 gig, go measure it. It won't be 40 gig. CPUs, half the time it's getting thrown off. It's just like it won't be anywhere near that fast. Stream is like, you know, running like crazy all day, all night, no interruptions. The real system doesn't work that way. So what we're trying to show is most people have an idea of what it's really like when the system's loaded. The reality is different, and therefore flash, which is a slower media, can do the job. Think of it in an abstract way. The page is far, and we got to bring it close, and we're going to do it in a certain amount of time, and then the application gets access to it. And in that way, you can kind of look at a multi-CPU system as kind of a similar analogy, right? The flash is kind of like the data is on a node that's a hop away. And that's why we're showing this analogy.
So it's all about not jumping across QuickPath all the time. That's what it's about. It's about reducing the number of times you have to cross the interconnect.
It's one of the biggest things, yeah, because if we can get the data to that thread local, it's going to go fast. And then it's even better if the application keeps using that data, right? Well, you take the hit one time, but then it's hot. And then it's just like it's all in RAM. So really this is about, and he'll talk about it later, a lot of this is getting the data at the right place so that the application can start chewing on it. You know, and if it's far, it's okay. Now we don't want 100 microseconds to turn into a millisecond. We don't want a millisecond to turn into 10 milliseconds. And so keeping it constrained to a certain order of magnitude of delta is very critical. And we'll show you later how the architecture can do that.
So you would, just to touch on that, I guess I don't know whether you're going to have a slide for it, but you're implying that as long as you've got application workloads that have a high data locality for a reasonable length of time, you're moving that data in, and then you're allowing them to access it, and then you're moving in another piece of data, rather than lots of data being moved in and out all the time.
So that's one aspect that will make it, that makes it work, and I actually have it listed as one of the things that make Memory1 and Flash is being able to use it as
So it could be very application specific, and you could find that the software vendors need to almost rewrite for your hardware to optimize it.
Well, let me put it in a slightly different way, and I hope that will answer it. If an application can fit all its data in a dual socket, one single dual socket server, which is the example you mentioned, you know what? That's probably not an application that will benefit from Memory1. We're talking about applications that cannot fit in one box. So they have one of two options. They either scale out the boxes, which is really bad now because you have networks and a whole bunch of issues, or buy a quad socket. That's why we're talking about the quad socket, because that's the next best performance that they can have.
And by the way, there's no web scaler that buys a quad.
Yeah, but you're talking about hyperscale customer. Actually, SAP HANA could be a better application for this, because you have...
Probably not better. There's only 1,000 SAP HANA systems that are sold in the world, but...
sorry?
There's only like 1,000 in the world.
Yeah, but theoretically, so you can have, it's easier, no, to implement for
We'll show you results on Spark, which is an in-memory analytics. It's like SAP, but cloud. Okay? And this stuff flies. And the reason for that, SAP HANA is a column-based, compressed in-memory database. The beautiful thing about columns is that when you do a query, you start here and you end there, and you do that n number of times, and then you do some kind of, here's the result. Well, the software that his team developed allows us to build up a lot of momentum in stuffing that data to where the processor needs it, and those queries happen very fast. And you'll see that on Spark, on the sort, where we're sorting a terabyte of data, but they're all built in these clustered RDDs, which are similar to a column-based database. And what happens is it goes like stink. And the reason for that is because we can learn and prefetch. Okay?
Sequential detect on memory?
So then I have another...
Sequential detect on memory?
Sequential detect and memory.
So you're doing prefetch of sequential access to memory.
We learn what the application does, and we can stream it in.
We'll touch on these, on the various
That is exactly how you achieve. We will show you the measured results. Critical, right? Critical. So
you can't just respond to page faults and just bring the page in. You have to add intelligence.
You have to learn what the application does, and you can predict with very high hit rate, 95% is what we're measuring, what data needs to be when. And if you have something like SAP HANA, the minute you detect that it's going to go and need that column, let me tell you, you can get it in pretty damn fast.
Okay, but then again,
so you're right, it would work
Spark,
very well.
you can have a single job running, but actually you can have also many different jobs running.
A lot executors, lots of executors.
Yeah, so at that point you can organize Spark to have the single thread pinned to a single core. which means that you have access to memory locally. So all this model doesn't work anymore.
Yes, until you run out of memory.
Yes.
Yeah.
And
The assumption is you
again,
can't
like,
if-
of course, you know, we're not competing with DRAM, right?
Exactly.
We're complementing DRAM, and you're right. Of course, it runs. If you run a job, and I'll show you, did a 140 gigabyte sort on 128 gig, runs in like half an hour, right?
No,
You add
this is
everyone,
totally
boom.
correct. So when Spark came out, the problem was disks, because they ran the first Spark installations on Hadoop, on whatever that was on
But I mean,
disks. And
you want the
it-
RDDs cached and persisted in memory in Spark. You don't want disk involved at all. The whole point of
Yeah,
Spark
but
is
the
not-
problem at the beginning was that potentially they could do 100 times faster, and it was just 3 to 10 because every now and then you go to the disks.
But you can net that out. Like, that's just an ingest data problem and throw out, you know, and persist the data out. If you net that out and just look at how long does it take to do a sort, a count, or anything like that in Spark, that's what you really care about. And most importantly, once the data is in memory, you can do all kinds of queries. Like, why would you sort the data? Well, you want to sort it so you can do something on it afterwards really fast. And that's what our customers want. We have customers that right now are doing like bake-offs on 10 terabytes. We're doing it like on 3, 4 machines versus 20, 30, you know, machines. Like, this is a huge consolidation, and we're going to show you the results today. It's real. So the whole point here is we're not going to be as fast as DRAM, and we don't care, right? We can get damn close, and we're talking now about 2 terabytes of pretty cheap RAM in a very high-powered server that's got 56, 72 threads. That thing can do a lot of work. And so we want to be good enough, save the customer tons of money, and do like a lot of work. We don't want to beat RAM, but you know, our software is intelligent enough that you can run it sometimes and get amazing results. Ask yourself why. Because you can predict, you can put the right things in RAM, and once it's in RAM, it will run as fast as it would before. So as long as you're smart about what's where, you can get amazing results. All right, so there's no smoke and mirrors here. It's just like a lot of hard work and really intelligent software and hardware. But you know, it's not smoke and mirrors. You got to get the data in the RAM, and it's going to work really, really fast. And you got to get the right stuff out and the right stuff in, and just shuffle it back and forth all day and all night based on what the application needs. That's how it works.
Yeah.
So you can probably move on.
Yeah, so just one last comment about this configuration is, as you can see, data is, the performance of the bandwidth is highly dependent where the data is coming from. And I know a friend, I was talking to him in a conference, and his job is actually to try to maximize the NUMA or optimize for NUMA locality and try to, through the OS, try to make sure that everything that's running has its data localized. And it's a very, very, very complex task. He told me, I actually shared with him these numbers, and he said, yeah, you know what, we can get slightly better than the worst case by doing a lot of work trying to localize for NUMA. So it's real, it's a real problem. As you scale, as you go out from the NUMA node and start scaling either by adding more NUMA nodes or start scaling out from the server, it's a real problem. You lose, your DRAM performance is not DRAM performance anymore. All right? So this is to address the bandwidth question. Now, next, DRAM is perfect. It's nanoseconds of latency. It's super fast. Flash is microseconds. Well, let's put that into test as well. Very similar to the stream test benchmark that we have executed. Unfortunately, stream does not give you latency, so we had to create our own homegrown benchmark. We call it Memphis. But it does very, very similar like stream. It does memory transactions, very, very lightweight on the CPU, and a lot of memory transaction. The good thing about it is it actually gives you latency measurements. So what we did is very similar exercise. We pinned the process in on node 0, and then we made it access data from node 1, node 2, and node 3. And that just measure the average, measure the latency, average latency, and we created a histogram of all the accesses we have seen. And in this particular one, we did equivalent to a queue depth of 1 storage, where we did not overload the memory channel. We're just doing one transaction, 1 4K at a time, and measure 1 4K at a time. We're not trying to congest the QPI, just to see, just from a latency perspective, as opposed to queuing perspective, what the latency will look like. Well, in average, we found that running in the same NUMA node, well, it's not tens of nanoseconds, it's actually hundreds of nanoseconds in terms of average. And for remote access with a very quiescent system, it actually all the way up to 1 microsecond in terms of average. Not only that, but we also found that these are the bars. So the red one, this is running with local to the NUMA node. This is node 1, node 2, and node 3. We found out actually there's decent amount of transactions, about 0.1%, that are actually more than 10 microsecond. And this is a quiet system, doing nothing. But yet the memory transaction actually took greater than 10 microsecond once it went outside the NUMA node. Okay?
So, I'm sorry, I'm trying to read this. The first chart is DRAM.
It's all DRAM.
It's all DRAM.
All DRAM.
And this is
similar configuration. And the
same-
second chart is Memory1.
It's a histogram.
No.
So this is averages.
There's no memory one. This is just DRAM.
These are all DRAM.
This is all DRAM. This is the average of the latencies for the 4 different scenarios, accessing from the local node, node 1, node 2, and node 3. And
yeah.
this is the average.
Okay.
And this is the histogram. So how many transactions took less than 1 microsecond? Local node, reading from the local node, well, almost a lot of them. This is logarithmic scale. So a lot of them were less than 1 microsecond. And then as you go away from the NUMA node latency, you get less than microsecond, more on this inside this bin. And of course, as you go to less than 100 microsecond, you have less local node and more on the remote nodes.
So what this shows is that, and by the way, this is not a knock, right? This is just to show you guys, this is the reality. It's a quiet system. You know, and really the latency here is, call it a microsecond. Most accesses are taking, with the exception of the ones that are local, are taking about a microsecond. This is educational, but there's no memory 1 in here, right? It starts getting interesting though when we load the server now, right?
Exactly.
So
And
the
another-
next slide is going to have when it's loaded.
The other comment, this is as seen by the application. We're not measuring at the
And
memory.
this is random or sequential reads of the memory?
the random 4K.
The random 4K reads, one at a
Random
time.
4K reads.
Queue depth of 1. So there's no, this is not 60 gig bandwidth, right? It's just a queue depth of 1. It's the best you're going to get.
Yeah.
We're not
It's
measuring
an
bandwidth.
honest test to measure what can I do, right?
With memory. Yeah.
And they're repeatable. The type of processor is there. There's no magic here. It's just on DRAM. In none of this is there any memory 1 anywhere. It's all DRAM. Okay.
The next one is now, of course, as you would expect, is actually loading the system and running as fast as we can, and now measuring the latency of all our transactions. Well, as expected, the average latency within the NUMA node, running within the NUMA node, went from 300 nanosecond. Now the average within the NUMA node is 1 microsecond. The average latency for remote nodes is jumped from 1 microsecond to 3.5 microsecond. We're not talking about nanoseconds anymore. Now we're talking about multiple microseconds in average. Well, not only that, but now we're starting to see some actually accesses that all the way up to milliseconds. So the idea that DRAM is
So like a level 1 or level 2 cache is really not helping here.
If you're doing random reads,
It doesn't
for
do
example,
anything. It
you're
doesn't
doing
help you.
Memcache or Redis or something on the internet, it's pretty random, right?
Yeah.
Stuff's coming in. This is the whole point. And the reason for this is simple. This is a coherent cache, right? When you write data, you got to tell everybody you're writing. Like, in other words, the more, and by the way, this is why I brought up the point about this architecture being in the new Haswell 2 sockets. The cache invalidation, very expensive, very expensive. So it turns out that when you start doing pretty random, normal application level stuff, this is what you're going to get. Right now,
These are
the
only
point is
reads.
this is
There's
still amazing.
There's no writes going on here. This is
There's
just
no
reads.
writes. There's only reads. Actually, the bandwidth, when you do writes, we have the data. I can send it to you in
It's
an
much
email.
worse. It's gotta be
Your
much
bandwidth
worse.
is going to drop to 3 gig when you start doing writes. There's only reads. They can't prefetch, they can't do any of the stuff that they do to get those amazing numbers. It's pretty random. And actually, we model all our stuff on random also. So the point here is just to show you cannot actually read data, a 4K page, in a microsecond if you're going across. It's 0. If you look at node 1, 2, and 3, it's literally 0. It's all in here between 1 and 10 microseconds. Now, this is still amazing, right? It's just to show, though, that when we're talking about what are realistic latencies and bandwidths, we're not talking about a nanosecond and 100 gig here, right? We got to get into the reasonable 10 to 100 microsecond, and we got to be consistent about it. And you know what? We can fake the application out to think that it's running in DRAM, right? So that's the idea. You can clearly see, by the way, the load we did here was just spool up more threads to the number of threads. It wasn't something crazy. But what happens is the system gets busy, the caches start getting invalidated, they start getting kicked off, and then all of a sudden, before you know it, things are taking more time than you would have thought.
Yeah, I mean, right? the fiction here is it's a log-log structure here. I mean, this number here that's 1 versus, hundreds of thousands or millions, it's so, I mean, it's happening. It's, it can get to a millisecond or something like that on the order of 4 or 5 accesses are that level, right?
No, but this is the number here, 3.5.
Yeah, but that's microseconds. You got milliseconds on this chart. The thing is,
Well, that's what we measured.
All right.
The point, it has outliers. It's not. It does go. Even if there's one.
Did you want us to not include them in the?
No. I'm just saying it's a log effective graph here that we're looking at.
Yeah. I mean, the key is 1 to 10 microseconds, right?
Yeah, I got not the far outside.
Right? And you know what? It did take a millisecond. And if you were the guy that wanted that 1K object on the internet, your object might have taken 10 milliseconds.
But
that's why when you run Redis,
a billion accesses, maybe there were 5 that took a millisecond.
True.
Okay, I'm good now.
Take a cookie.
But if you would have had to bet, would you have bet that it would have taken an average of 3.5 microseconds?
Why? No.
Okay, well that's what we're trying to get across.
And similarly, would you have ever thought that a memory transaction can take up to 3 milliseconds even though it's like 5 out of a million? People never thought that a memory transaction can be milliseconds.
And actually, when you have
and that's what we're trying to highlight here.
70 threads at 3 gigahertz, 1 out of a million happens pretty fast. So, but here's the point we're trying to make. We're trying to say that memory is a little slower than what you probably imagined, okay? And this is measured data that's done without, pretty objectively and can be repeated, and we don't mind sharing the results. And it's only reads. Nobody's doing 50-50 or anything like that. If you do start doing writes, let me tell you, it all gets pretty out of whack. So we kept it to just reads, to be fair, right? So now, we can start looking at, where do we want to be? And we want to get in the zone of having our flash approach 10 gigabyte per second. And we want to try to keep that latency as near to 100 microseconds as we can. And that was our design target. And that's been working for us, right? A lot of the applications that we run, if we get into that zone, like for example, Spark, is running, and we can see that, 5, 6, 7 gigabytes on the flash. And actually, we're sorting extremely fast, and it's working extremely well.
Yeah.
So we wanted to give you what our design points were, so that the question is, well, how does it compare to RAM? Well, we're slower, but let's be fair about what we're comparing also.
Yeah, but you also have, you're driving the RAM memory as fast as it possibly can. In that last scenario, you were hitting it with whatever number of threads were potentially, the one before that, which was kind of just normal access. And if we're talking about, a workload like a database and memory workload, you're not going to be hitting this memory as fast as you possibly can, I don't think.
Well, it will not be one at a time. This is really ideal. So this is really low
Yeah, I understand. You're driving this thing as fast as you possibly can, and you're getting this 300, 1 to 10 millisecond, microsecond response time versus I'm driving it like on a more normal case of situation, and it's now 350 nanoseconds. So it's kind of an edge case in my mind. Let me ask the question. Maybe I shouldn't ask the question. I should.
Let me
ask the question. When you have your Memory1 solution in one of these, customers of yours, how fast are they driving the Memory1?
Well, it's pinned to the max.
Yeah.
We have slides for
Yeah,
that.
it depends on the application. Depends on what they're
I
doing.
know, but now I'm trying to understand your point.
Yeah.
When we are running, we're going to show you the data. When you've got 200 instances of Redis, I'll pick something simple, right? Like Redis or Spark, when you have 16 or 20 executors that are going, and you tell Java, hey, I have 48 cores. Well, I see the utilization go up to about 90% on the system. And I'm pretty sure that it's
Looks
in
like
this
that.
situation. And honestly,
if
if
it
you're
had been all
buying, if you're
memory,
spending
yeah.
$10,000, sorry?
If it had been all memory.
Well, Spark is an in-memory analysis engine, and it has every gigabyte of data stuffed with something that you're trying to analyze. Look, we're dealing
right.
with very high
not for
utilization
everything.
cases.
Like you're not using this as an archive for data that would normally go on tape, and I'm not using this for just my SQLite database that sits on my laptop while I'm doing dev stuff. This is it's an edge case. I see this as kind of a new market layer in between where this is for people who are doing high performance computing and stuff where they really want to push the thing hard, but I can't put as much memory into the thing as I would like to do.
Do you think this is an HPC solution? I don't think it's an HPC
No,
solution.
this is web scale. This is
more of a hyperscale.
Memory database.
So also, if you are going to buy the SSD, for example, because you don't have enough memory and you need a very, very high-speed storage.
Yeah. Flash is too slow.
Flash
Memory costs too much.
close
is
to
not
the
storage.
CPU is just because memory is storage now.
This is not persistent.
Correct.
This solution is volatile.
Because Spark manages the consistency. Spark works on copies.
Yep.
So
But then it's
it
even
doesn't care about consistency, okay? Because
where are the copies?
it always works on copies.
So the copies
So
are
the basic. So I'm not
I can
database,
explain it
I don't know.
if you-
But the basic of Spark is copying data before doing the transaction.
Is
Well,
it
the way
more
it's
simpler to
analyzed,
say
it's
it's
spit it out.
for memory optimized things?
Yeah.
And I'm going to be very vague there. And what's new in memory optimized things in this world is database stuff, like Spark, like Hackathon, like HANA, like
well, those
anything
are
new Hadoop.
those are business
And
intelligence.
it's probably a very edge case of even that. So, and then I think your cost benefit risk model, otherwise the architecture model for this, is for certain use cases of it. And I think that's where all this vagueness and everything is.
So maybe you guys can explain to us who your customers are. Like, what's the use case? What are they doing with this? Maybe that'll give us something more concrete to
Yeah,
get
of
our
course.
teeth into.
So, okay, a lot was said. So I'm going to start there and go there, okay? The way Spark persists is that there's a concept called lineage. So every time something is done on something called an RDD, which is a resilient data structure, it writes metadata to storage about how that new thing was generated, okay? And so if for some reason you lose all of the constructs that are in memory, you can go back and see the lineage and then recreate it from the first thing that is available to you. So it's lineage. It uses storage very sparsely, but what it does is it just keeps creating objects in memory, which is why it's very memory intensive. However, when you go to do queries, it now can recursively take advantage of the new stuff that's available to it and goes very fast, okay? So they use something called persistence in memory. That doesn't mean that the object is being written to storage. It means that the lineage of that object is written somewhere in storage. All that means is if you started at 1 and went to 2 to 3 to 4 to 5, if you lose 2, 3, 4, 5, it'll say, hey, it all started from 1, and you can recreate it in memory. That's really sparse in writing to storage. It doesn't depend on storage performance at all. Okay, so that's how they do, which is actually really smart. To your question, I think at the beginning, the gentleman asked, hey, are you betting the farm on the big companies? The market is not Hackathon or even times 10, right? The market is hyperscale. And the reason for that is because a lot of these guys have hundreds of thousands of servers that are doing key value, which is basically like memcache, key lookup in search.
Yep.
They have hundreds of thousands of servers that are doing sorts on user data, mobile user data, internet user data, to sell you ads, right? To go kind of do ads. And so the product is very useful for companies that have thousands of servers that are in the caching tier of the internet that are trying to get money out of your pocket. Okay, and that goes, from an Amazon to a China Mobile to anybody in that ilk. And it's very important to be able to do memory functions, right, and not pay the cost of memory.
Okay.
Right? DRAM functions and not pay the cost of DRAM.
So in
it's
that
critical importance.
So let me see if I can summarize a little bit. So I've got lots of this stuff, so I don't want to pay for RAM everywhere, but I need high performance because SSD is not enough. Would that be accurate? SSD is not fast enough, which is why I want memory.
Well, how would you use SSD? You can't just plug an SSD and make it look like DRAM. That's the first thing.
So I need RAM type behavior.
And by the way, all these servers still need storage, right? Because you still want to save the data. You want to do that in the cheapest way you can. Jelly Bean SSDs, commit to a file system, a distributed file system most likely, very distributed across tons and tons of servers, which is still running on flash, but it's still a distributed, some kind of, widespread storage type mechanism like HDFS, right?
So I'm still going to be doing some sort of I/O out, like I'm going to be doing I/O to disk, and I'm going to be doing I/O out across the network and so on. So my use case isn't trying to get as much possible memory as I can that will always be local to that one socket that runs that one thread because I'm doing a massive data analysis thing on this thing. I just need lots more RAM. Is that right?
Yeah.
Okay.
And
I think.
then you can jettison the data, right?
I mean, to
Jettison
me,
the data and move on.
it sounds like we're overthinking what it's really doing. I'm just going to say it.
It just sounded like because we're focusing on this non-unified memory access.
You're talking Redis, you're talking all these memory-intensive applications, and all I'm trying to do is minimize the cost that it takes to get the memory to be able to crunch the data. I mean, is that to say it simply?
Exactly. Yeah. And instead of having to scale out
Right.
multiple servers or having to do multiple sockets,
Right.
you stay in the same dual socket, cheap flash, and you can do the same amount of memory.
And what we were trying to say before was that you have to get into a reasonable zone of performance before it starts to blur for the customer, right? And you need the flash and you need the system to have a certain level of performance.
You need to be good enough.
We were trying to show, well, what is it that could theoretically be good enough?
What's that number that makes
right?
sense?
And that's
where
why the
it's
4-socket
cost
analysis
versus-
is.
Exactly. What is good enough? We're trying to quantify
And actually,
that.
we're seeing that. As our stuff started to approach that 6, 7, 8, 9, 10 gigabyte number, which, by the way, for a storage subsystem is ridiculously fast. Think about that, right? When it started getting there, everything started to kind of zone in really nicely, and then all of a sudden the customer is very happy and they can't tell the difference anymore, right? The network is now the bottleneck or something else is the bottleneck, and we're just not the slow thing anymore. We're faster than everything other
Well,
than
it's
the
like
CPU.
anything else. It's going to warm up with data, so it's going to be
Exactly.
more resonant data.
So
That's going to be in memory.
there's some validity to the analysis, right? And then the question becomes, okay, well, something like 3D Crosspoint, for example, is significantly faster. Well, now the gap between what the customer will see is pretty small. And that's what's important. Like, what's good enough? Why do most of the web guys go with Jelly Bean SSDs versus some of the high-powered big, SSDs that are so much faster? Well, because they don't really need all that performance. They really focus on cost and just good enough flash performance. So this is about, unfortunately, our flash memory being good enough, not the best. Right? That's kind of what it's about.
And that's understandable. And there's a price performance calculation that anybody who's buying this equipment would make.
Exactly.
So toward that end, you got some idea what the comparison in pricing between memory and the Memory1 equipment, what sizing looks like in a DRAM module versus a Memory1 issue?
I could tell you
Are
that.
there, for example, configurations that are required? So you need parity, or you need X memory versus X Memory1. How does that exactly work?
So this is the answer.
Okay, I remember the slide.
Okay, so you asked about the ratios. They're fixed. They're 1:8. Okay. Those are the configurations the customer can buy. In general, I'd say depending on who the customer is and how much they buy, we're anywhere between 30 to 50% today of the cost of a Jelly Bean 16 gigabyte memory module. So we have 8 times more capacity, and we're 30 to 50% of the cost on a per gigabyte basis. And that's because today there's nobody else on the market.
And don't forget in memory.
So it's the first generation of the product. And you know what? We're going to streamline our own costs, and we're going to converge to something more aggressive over time. But that gives you a flavor, right? You can stuff a 1 terabyte box with about what it would cost you to put 200 or 300 gig of normal RAM in there.
It's really good information.
It's a pretty big cost delta. And I want to remind people, at 1 terabyte, $1 per gig is $1,000. Right? So in the old days, hey, I pay $9 or I pay $10 for 128 gig, it's a $100 difference. I don't really care. At 1 terabyte, when you pay $1 less, it's $1,000. You pay $2 less, $2,000. So when we talk about, hey, they're at like $3 a gig, and I'm at $6 a gig, and DRAM's at $9 a gig, that's a $4,000 difference in the price, which, by the way, is a half a server. Right? So we're getting to the point where we're in 1 and 2 terabyte capacity points, and we're talking about $1,000 at a time, and that matters to customers.
So real quick, and then
Does that answer your question, by the way?
That's a perfect answer.
Is there any reason I can't use this in my hypervisor? I'm going to just throw KVM out there because it's probably going to be the easiest way to manipulate the memory. Or is there not a use case for this? I mean, obviously, it's still...
There's no reason you can't do it.
You can't, right? I mean, there's no reason you can't do it.
But would you get anything from doing that, though? That's the question. I mean,
Well,
sure,
you
you
wanna run
could
your
do
containers.
it, but...
we see people in the cloud
Right.
trying to move away from hypervisor, try to use more container, trying to write
Exactly, that's why I'm saying...
ways of splitting the CPU without the overhead of KVM. We just had this
Right.
discussion this morning with somebody.
Yeah,
It works. It's not the trend I see.
sure. It was
Right?
just
I see
purely a
these
question
guys
like...
wanting to get closer to the metal, wanting to stuff way more capability into the system,
Yeah.
use the threads way better, and do away with the bloat of virtualization. It will work 100%. It's working today. There's absolutely no reason KVM doesn't work. It's working already.
So, I mean, literally, you could just stand up your bare metal and run all your containers and just get your memory that you need for all your little containers.
People are doing containers.
Okay.
What is it that I need a special server for? Because it runs, it's DDR4 compatible DIMM socket, isn't it?
Yes.
Yeah. So what do I need to have a special server with Magic in it, or could I buy some of this and whack
Any
it in my
server,
DDR4?
the only thing you need is a BIOS support.
You need to buy it from a vendor that has integrated this into the server, which
Okay.
means that they have a BIOS that supports it.
Okay.
That's it.
What is
As a
that?
user, you don't have to worry
And it's a
about
channel of distribution that you guys have set up as to that's how your channel to market works. Okay, cool.
How much of that specialized BIOS cannibalizes your price point, your price advantage?
Nothing. The BIOS is available from AMI for free.
Yeah.
The OEM compiles it.
Is
and they have
there
Memory1
a
supported
premium
cloud.
from the vendors?
Sorry?
Is there a premium from the vendors?
Look, that goes back to back to the price, who's buying it. Different customers have different purchasing power, different arrangements with vendors. You know, in the case with something like Supermicro, you know, you would get it through them, and of course they would have a markup on that. It's only normal, but they're marking everything up, right, including the DRAM. And so everything I talked about before will hold, more or less. A lot of the web scale guys are doing more consignment stuff, honestly, and so it's a different business model, as you can imagine.